All right. Hello, everyone. Let's finish up the examples in the 2.7 notes. So, number 36, Hendricks Publishing Company. They want to design a page that has a border all around it, and they give the dimensions of the border. And they're surrounding 40 inches squared of print material, and X is the width of the print material. So, let me get a little thicker here. Here's my print material. The width is X. I know area is length times width. My area is 40 square inches. My width is X. So my length is going to be 40 divided by X. Now we have the border. We have 0.75 inches on this side, 1.5 inches on this side. So if you can visualize it, the border is like this. And then the other two parts are inches, and this is not drawn to scale. It's just my rough sketch. And they want us to come up with a formula for area for the whole page. So if I'm looking at the width of the whole page, I have X plus 75 and 1.75. If I'm looking for the other dimension, I have 40 over X, and I have 1.5 and 1, so that's 2.5. So X plus 1.75, 40 over X plus 2.5. And this is one of those cases where you're wondering when you're going to be able to use your calculator. This is something I would expect us to use a calculator on. I'm not expecting you to FOIL a crazy binomial with decimals and a rational function. So let's go over to Desmos. And I have them already typed in here. And notice this is a picture of the relationship between the x-axis, which is the width of my print material, and the y-axis, which is area. Well, what was the question asking us? Let's go back and look. Express the area of the page as a function of x. We've done that. Find the dimensions of the page that has the least area. So we're looking here, and will I want to go in the bottom left here? Well, those are x values that are negative, so while mathematically they might make sense, realistically, you can't have a negative width, so we discount that. That's an extraneous solution. So we look up here. We know the x values are the width of our print material, the y values are area. We want to have the least area, and so we're going to find the lowest spot, and the lowest spot is 5.29 for the dimension, for the x value, and it's 70.83 for the y value, which is our area. So what are the dimensions of the page that has the least area? Well, the least area is that 70.83 when x equals 5.29, but that's not just what they asked for. They asked for the dimensions. So I actually have to plug in 5.29 plus 1.75 and 40 over 5.29 plus 2.5, 5.29 plus 1.75 gives me 7.04, and 40 divided by 5.29 plus 2.5 is about 10.06. So the dimensions are about 7 inches by 10 inches. All right, the last example. fuel economy. The weight of a vehicle is a major factor in its fuel consumption. The table lists the weights and gas mileages for 2016 Ford model, and they tell us a model for this data is given by y equals 238,300 divided by 2x plus 1. Remember, y again is the fuel economy, and the x is the weight. So weight is x, fuel economy is y. This gives us the relationship between fuel economy and weight. Now, graph the model together with a scatter plot of the data. So let's go to our graphing calculators. And let's graph a scatter plot of the data. So I'm going to go to my table. And I should have cleared all this out before. This is from statistics class. We'll just get rid of it. And let's do our data 2952, 3472, 3531, 3912, 4439. Then I have to look at my data again because I usually must type something. Then I'm going to do the gas mileage, which is 40.45. Enter. 2952. All right. 40.45. 3321. 3307. 3140. And 2618. Double check it over real quick, make sure nothing looks crazy. Make sure there's no equations in your y equals. I'm going to graph. Oh, I got to turn my plots on. So plot, I turn on. I want a scatter plot. My list is from L1. Press zoom 9 to fit your data. And sorry, I've got plots from statistics class still going on here. All right, this one's off. Is this one off? That one is off. That one is off. We have on. We have list 1. We clear that out. All right, now let's graph it. Press zoom, press 9, zoom 9 helps your data fit to the screen, and there's the plot of my data. Now I want to plot the equation on top of it, so now I go to the y equals, and I want to graph that equation, which was, I believe, 238, 300. Divided by, and then I'll put in parentheses, 2x plus 1. Now I'm going to hit graph again, and it looks like their model, their mathematical equation fits that data pretty well. It fits that data pretty well. Now, use the model to estimate the improvement in fuel economy only a manufacturer could achieve by finding a way to reduce the weight of a current 3,200-pound car by 100 pounds. So we're looking at the 3,200 pound car. And if we reduce it to 3,100, how does the fuel economy go up? Well, let's use our graph. We could plug in the values, but let's use our graph. So we're going to go to trace, and I'm going to turn off my scatter plots. Or wait, maybe there's a way. Can I trace my graph by touching it? Nah, I'm going to turn my plots off. So I turn my plots off. Then they won't be in the way of my graph. Now I can trace points instead of, or trace my graph instead of my points. I want to go to, I think it was 3,200. So here's 3,200. Close, 3,202. So 3,202 looks to be about 37.2. And if we go to 3,100, we get it to be about 38.5 for my gas mileage. Well, 32 was about 37.2 miles per gallon. 3,100 was about 38.5 miles per gallon. We can calculate that directly. So if we find F at 3,200 from our model, 238 300, 2 times 3,200 plus 1, and we can find the gas mileage for a car that's 3,100 pounds. That's 238, 300 divided by 2 times 3,100 plus 1. And now let's calculate that. That is 238, 300 divided by 6,401. And I get 37.2, very similar to what we had on the graph. 238, 300 divided by 6,201. And we get 38.4, very similar to what we saw on the graph. So I take 38.4 minus 37.2. I get 1.2 miles per gallon is the increase in fuel economy we have when our car is just 100 pounds lighter. So there you go. Using a rational model to model our data, and the reason we always use our data then is to project what will happen now that we have a great model, a great equation. Let's use that equation to project what's going to happen with new inputs.